Hey, howdy everyone, we're back again. It's been a little while since I recorded a video. I've been quite busy with a lot going on, but the class is rolling forward. We got a lot of good stuff going on with the project team, so let me get into this and provide a resource for those students and for anyone else out there who's interested in following along with us. We welcome you very much. So what we'll do now is we'll talk about univariate statistics. And so we've already talked about, we provided an introduction to the course. We talked about some fundamental prerequisites, a bit about data preparation, and of course a lot of philosophy about subsurface modeling, how do we build models, documentation, and best practice, and so forth. And so now let's get into univariate statistical analysis. Now I'll note that those of you who are interested, there are videos for the undergrad course that do have perhaps more details. If you're interested, you can go ahead and check that out from the PGE 337 course on Introduction to Data Analytics and Geostatistics. It has a lecture specifically similar to this one, and also there is a lecture I will not cover, which is on fundamental statistics. And so that gets into measures of centrality, expectation, the mean, the mode, and so forth, and also dispersion, measures like standard deviation, variance, and so forth. And so we won't cover that in this course, but just ask you to go back and check out those videos. This is a graduate level course. We are really focused on subsurface modeling, and so we want to get right into the topics that impact us in subsurface modeling, and some of it we'll just ask students to watch videos. And so when we're talking about univariate statistics, let's recognize what we're doing here. What is the actual motive we have? And it's all about data analytics. And if you look up the definition for data analytics, you'll find a variety of them, and they're pretty similar. There's pretty good consensus around this, that it's the process of examining data sets in order to draw conclusions about the information they contain. And specifically, they might note that you're being aided with specialized systems, software, tools, methods, workflows. And so if you look at data analysis, it's closely related. It's more the action of inspecting, cleansing, transforming, modeling data with the goal of discovering useful information and informing conclusions. Now, any good definition related to this should have the term decision making, because as we've talked about before, if what you do does not impact a decision, then it really doesn't have value in general. So, and data mining, of course, is more of a kind of a specification of these terms where we get into the idea of data analysis techniques that focus on modeling and knowledge discovery for predictive rather than purely descriptive purposes. And so when I read these definitions, I hear in the back of my mind the definition of statistics, which is of course all about the process of gathering, pooling information, making useful summaries of that information, all for the purpose of supporting decision making. And so to me, this all becomes very united. We are working in an area of statistics, which is data analytics, or what I could say is in order to do a good job in data analytics, you want to understand fundamental statistics. Concepts like the fundamental probability, concepts that we talked about before, Bayesian, frequentist frameworks, and so forth. So let's talk about displaying data. The most simple univariate display or way to look at our data is a statistical distribution. And so definition, a distribution of a variable is a description of the relative number of times or frequencies each possible outcome will occur in a large enough set of trials. So it always comes down to we have enough samples to understand something about the underlying population from which we're sampling. And so what do we get from a statistical distribution? Well, this is an image or schematic of a statistical distribution right here. Maybe we drilled the subsurface and we found out the porosity values for a variety of samples. We compiled them and we put them into what we will term later on as a probability density function, a PDF. And so this is an example of a statistical distribution. What do we gain from that? Well, it's very useful. You see on the x-axis, you got the actual values of porosity. And so you can look immediately and you can see this is the minimum, this is the maximum over here. Very useful. You know the range of the values. But beyond that, you have an understanding of, do you have a lot of low values? Well, in this case, it looks like the mode is pretty close to the low side. We actually have quite a few lower values. And we'll see that the distribution is positively skewed. So there are not that many values that are high. We get up to about 20% porosity, but you can see there's not very many of them. And this is pretty powerful. In addition to that, we may have a distribution where we have maybe some values out here. And we can start saying, visually it looks like we have outliers. We need to explain that. We need to look at that data, make sure something didn't go wrong. Or we may want to apply one of the tests like Tukey's test for outliers to determine whether or not, in fact, it is an outlier. So let's also think about what is the importance of a univariate statistical distribution. Why do we look at them? What is it telling us? So it tells us about the range, the relative frequencies. That's good. I like to also state that it is, in fact, a predictive model. If you imagine, we've sampled the porosity values all over the subsurface in the area of interest, that volume of interest. And now we have this distribution. Now, if we move to another location within that same area of interest, but perhaps far away from the other data, this statistical distribution becomes a predictive model. We could use this distribution to say, hey, you have no other information. This is the maximum amount of uncertainty we have. It could be anything between 10 and 20% with these relative frequencies. So really, we can look at the statistical distribution as a model of uncertainty that we could use globally at locations away from available data to us. So this is very useful. Now, of course, if we have local information, it will be updated. It'll be updated by local well data. If we have a well value that has a porosity that's very high right beside where we're now looking, we might say, well, this global distribution isn't quite correct. We expect it shifted high, and we can do that. We can use spatial estimation methods. But remember, these statistical distributions represent uncertainty models. Globally, away from data that's available to us within the area of interest, and locally updated by local sample information. Also, locally updated by local trend information. Now, could it be biased? Yeah, of course it could be biased. And we will talk about all of the issues around data representativity. We'll have a lecture on that and how do we correct for that. What about scale? Every time you look at a statistical distribution, recognize that it has an area over which it was sampled and an implicit scale. In fact, if we were to increase the scale of the sample sizes, what they would call the support volume of the samples, you would find that the distribution variance would in fact shrink. It would decrease. Now, of course, this is schematically drawn. The area under the curve has not been standardized to equal 1, and we would expect these peaks to start to increase in height as they start to narrow. That's fine, but it does communicate the idea. So, represent these statistical distributions. Well, there's a variety of ways we can represent them. And so the histogram is the most simple form of all. And what we do in a histogram is we just simply take the range of possible values, say porosity between 0 and 20%, and we bin it. We cut the data up into equally spaced bins. In this case, we go from 0 to 20, and we have about 12 different bins. We've sampled it on basically equal spacing, and we're able to then look at all of the data and just simply count. How many times did you have a data value in each one of these bins? And if you look over on the y-axis, it simply is frequency, just the raw frequency. And so 1 data in this first bin, 3 data in this next bin, 2 data, and you can see what I mean from there on. The probability density function is different. It is a representation of the probability an outcome has a value equal to x. Now, if we look at a probability, the most simple form of probability density function is the one that's binned. We can bin the probability density function and we get what's effectively a normalized histogram. And so now all we've done is we've taken each one of these frequencies up here and we've divided by the total number of samples. And by doing that, what we've done is we now have the probability of being within each one of the bins. This is a binned PDF. And so what's the closure relationship? Well, in general, we'll know that the PDF values, the sum or the area under the curve will be equal to 1. And for the case of binned or discrete representations like we have here, we could sum all of the probabilities. This is about 0.05. This is about 0.1 0.15, or so 5%, 15%, and so forth. If we sum them all along, we'll find out that they total to 100%, and that makes sense. If you think about it, all possible outcomes are represented in that range, so the probabilities sum to 100%. For a continuous PDF, which we'll show next, you integrate between negative infinity to positive infinity over the density function, and you will find the area under the curve is equal to 1. So how do we know our PDF is valid? What's the rules? Well, in general, it will be valid if for a discrete case, for every one of the bins, the probability values associated with a bin is between 0 and 100% for all of the bins K. For a continuous case, we simply need a continuous representation of a PDF. We need these values to always be greater than or equal to 0. We also need to be able to state that for the integration between any two cases, in other words, what's the probability of, let's say, for example, being between 4% and 2% per hour, that value is in fact the probability of being between those two values in the continuous variable case, and therefore must be greater than or equal to 0 or less than and equal to 1. So it's a true probability value. And so those are the rules that we have. Now, how do you generate a bin PDF? Very straightforward. You take all of your data and you sort it in ascending order such that all of the values go from the smallest to the largest value. You divide the data range into a desired number of bins or classes, categories, and you go ahead and you then count the number of data that exists within each one of the bin. Now we sorted it because then it's easy to cut the data up. Effectively, if you use a computer and you loop over and you do some type of conditional statement to test, you wouldn't need to sort the data in advance. And then all you do is you count the frequency of number of data in each bin, and you simply take that and divide by the total number of data, and that gives you the probability of an outcome in each one of the bins. Now, for plotting purposes, it's very convenient to pick a mid-range value for each bin, like I've done here, and report it based on the mid-range values, rather than say that this bin right here is between 1 and 3% porosity. We just report it by the center of the bin, the midpoint of the bin, which is 2% porosity. Now, given what we just talked about, can you identify which one of these PDFs, continuous PDFs, are in fact valid? I'll give you, well, you'll take as much time as you want. You can pause me. I'll count to 3 and then I'll go ahead and give you the answer. 1, 2, 3. So how's this one down here look? So we look at it for any possible integration of this curve. If I pick any 2 points and I calculate the area under the curve, it's always going to be between 0 and 1. It's never going to be, I know it's never going to in fact be negative, and so that looks valid. How about this one right here? The problem with this one right here is if I pick this location right here, the intercept, and this location right here, let's say that that is maybe about 16% porosity, this is 16.5% porosity. The probability of being between that point and that point is in fact a negative probability. That's invalid. You can't have negative probability. So this one's not okay. What about this one right here? What do you think of this one? Well, many people will think it's not valid. But in fact, if you look at this scale right here, and the numbers go between 0.1 and 0.2, that means this length right here is only 0.1. And so if you imagine even a uniform distribution, you would in fact need to reach 10 as a density value in order to get the area under the curve to be equal to 1. And so in the case of a continuous PDF, no, this 1 right here is not a constraint on us. We can go above it. It's really all the probabilities are all about the area under the curve over an interval. That's why we call it a probability density function. It's not giving us directly, it's giving us the density instead of the probability. Okay, so let's think about this case right here. If I pick this intersect right here, which is about 12%, and this one maybe 13%, that's just 1% between here and here. If I calculate that area, that is certainly not going to be above 100%. In fact, what I would suggest is that this curve might not be valid just from the standpoint that the area under the curve is not getting to 100%. Now, of course, we could say that about all of these curves right here, but they were drawn schematically to be illustrative, so it's good just for us to consider that. Okay, what about this fourth case right here? What do you think of this interval right here to here? So let's say that's 12%. Now, let's say that's 14%, that's 16% right there. What's the probability of being between 16 and 14% porosity? Well, the area under the curve is equal to 0. There's no probability. So this curve right here, this PDF is completely valid. It's okay to have 0 probability over an interval of values. Okay, so there's a little bit more details about what I just said. And let's go on. We'll keep moving on. What's the impact of bin size? And so this is a very good question. Does it matter what size of bins we use? And the answer is yes, it does. It's actually very important. And so what happens if you use too large of a bin size? You're going to mask important information. And so you could imagine this is pretty big. Imagine you made it even bigger. Ultimately, at the end member, you make it so big all the data fall into one bin and you don't see any information whatsoever. What about small bin size? Well, the smaller the bin size, what will happen is you have fewer data in every bin, so the statistic, the proportion or probability to be in a bin, becomes more unstable. And so you have too much noise. So, too small of a bin size, you get too much noise. Now, you take it to the end member where you go very small bin size, you'll reach a point where it looks uniform because all of the data will have their own bins. There'll just be a bunch of sparsely sampled bins where there'll just be one data per bin. So what's the solution here? You've got to balance smoothing out noise with being able to see information in the distribution. So you're going to choose the highest resolution with the lowest amount of noise. And so that's the challenge that you have. And believe me, people have done PhDs on exactly what bin size you should use. I'm sure very interesting studies. But for us, we will use this type of balancing act in our minds in order to try to get a reasonable bin size. Now let's talk about cumulative distribution functions. I like cumulative distribution functions, or CDFs. They're very useful. They're simply going to be the integration of the PDF. So the PDF is a lowercase f for a variable, and the CDF is represented by an uppercase f. And so we integrate from negative infinity to an x value. We are calculating a CDF. And if you think about that, all we're doing is calculating the cumulative probability from the binned or from the continuous probability density. And so this is pretty straightforward. We can go ahead and apply this methodology. Now what you'll find is if you look at this binned PDF right here with the frequencies recorded, and this is in fact probability over here, if we calculate the CDF, the first thing you'll notice is that the CDF must be monotonically increasing, because as we move across, we are adding additional samples. We can't take samples away, we can't have negative probability, so this cumulative plot is going to continue to increase. Now, if there's no data values at all over a range of values, what will it do? Well, it will just simply go level. And that's okay, that can happen too. So we know that it's going to be monotonically increasing. The other thing too about it is that the CDF is really a continuous representation which doesn't have any binning associated with it. In fact, if you think about it, you're just going across here and you just go up every time you find more data. So you don't have to make a binning assumption, which I like very much about this CDF. I'll show you also the fact that it's a mapping from cumulative probability directly to data values, which makes it very convenient for getting those values. And I'll show you right here. So how do we use the CDF? Well, the first thing we can do with the CDF is we'll recognize that the CDF value so the f of x, so if we take a value of, say, about 24% porosity, and we go ahead and calculate its CDF value as 52%, that is the probability of a random value being less than, from this distribution, being less than or equal to that threshold, to that actual data value. So the CDF directly provides us with the cumulative probability value. This should be probability right here. Sorry about that. And so it's very powerful. What's the probability of getting a porosity value less than or equal to 24%? It's 52%. So that's pretty powerful. That's very useful to us. We can also use it to calculate the probability of falling within an interval. And so this is pretty cool. We can say, what's the probability of being between about 26% and 15% porosity? And the way we solve for that is we simply calculate the cumulative probability of the upper, which was the 26% porosity, and that's 68%, right? Right here, 68%. And we subtract from it the cumulative probability of the lower bound, which was 15% for A. Put 15% in here, we come across, we get 12%. 68 minus 12% is equal to 56% probability of being between those values right there of 15%, of 26% and 15%. And so that's very powerful. We're able to work out these probabilities of being within an interval. Finally, we can go backwards. So if we take the cumulative distribution function represented by capital F of x, which for us is porosity right here, and we do the inverse of it, we're not going this direction, we're in fact going this direction. And so with the CDF, we can look up directly any cumulative probability we want to work with. So we could calculate the P90. Many companies will use P90 as being the value for which 90% probability you have even a lower value. Some companies reverse it and they call that a P10. I'll use the method of P90 being all values, 90% values being less than. So in that case, we get the P90 value. We come here to 0.9, go across, come down, 28% porosity. That's our 90th percentile for our porosity distribution. That's very powerful. We can get that directly from our CDF. So what I'll do here is I'll give you a chance to work a couple of these values using this provided CDF. Just do it graphically. You could just estimate it based on the screen. That's fine. We're just trying to understand. Now, of course, if we were doing this numerically, we would take the actual values within the CDF. We would use some type of interpolation method. If we had enough data, we don't need to interpolate, and we've just got enough to sample it. So go ahead and try to work this out. I'll give you, well, take as much time as you want, of course. I'll give you the answer in 3 seconds. 1, 2, 3. So what we have is, first of all, what's the p-value, or the probability, I should say, of having a porosity less than 20%. And so we can go ahead and we can go from porosity 20%, we go up here and we find it's something around pretty close to 30%, maybe 28%. What's the probability of porosity less than 26%? We can go up here, and we get something that maybe we'll say about 67%. What's the probability of being between those? Well, we already looked up the probability, cumulative probability for each of them. We just have to subtract them. So we take 67% minus 30%, and we get about 37% or so. What's the P50? Come over here to the 50th cumulative probability right here. We read across, we come down, and we get something around 24%. And the P20, and we've got it, about 18%. So pretty straightforward stuff. Okay, so now that we know about CDFs, let me ask you a question. Which ones of these are valid CDFs? Okay, I'll give you the answer in 3, 2, and 1. Okay, so how about this one right here? We've got a bit of a continuous linear behavior. It starts to roll over, and then it looks linear again. It reaches 100% here. Okay, so it goes between 0 and 100%. Good. It's monotonically increasing. I don't have any problem at all with this CDF. The CDF is perfectly fine. This one right here, we got a vertical line, and then we have a discontinuity, and it rolls over and it reaches 100%. Is there any problem with this? What's going on with the PDF to make that shape? Okay, so what's happening is you have a big spike. Probably 80% of the data values have a value of about 10%, 9% or something like that. So you have a spike. So whenever you have a spike of values, it will cause a vertical line in your CDF. And you can tell how many values in the spike by the distance on cumulative probability from the beginning of the spike to the end of the spike. So about 80% of the data are all the same value. Then you have a bunch of other values trailing off into the distance, and there's a few values on the high side going up to about 20%. That's an okay CDF. Everything's fine. What about this one right here? 10% up, flat, no slope, back up again to 100%. That CDF is okay too. What's going on between about 12% to about 17% porosity? No porosity values. And so we've got probably the PDF would be a bump and nothing in between. And that's a perfectly okay CDF. What about this one right here? Well, this is the one where we go, something's wrong here. And so we rise up, so far so good, so far so good. But then from here to here, we have negative slope. The negative slope would indicate that we have negative probability, which is not possible. And so there's something wrong with that CDF right there. Okay, how do you generate a CDF? You take a raw set of data values. How do you make it? Well, we're going to sort the data. This time we really need to sort the data. That's critical. Don't leave this step out. You sort the data in ascending order. You assign a probability value to each event. Now, if the data is unweighted, you don't have any type of declustering, which we'll talk about in a couple lectures from now, then it will usually be equal weighted. And typically there'll be some type of assumption. A very simple assumption that can be used is that it's just equal weighted, and the weight will be equal to 1 divided by n. And so you could do that. That's perfectly okay. And then you can integrate by summing the probabilities over all of the values that you have. And so you need to calculate the cumulative probability to assign it to each one of those data values in ascending order. And so if you use if you use the equal probability assumption, 1 over n, then the cumulative is simply going to be I, the index of the value in ascending order, divided by the number of data. Now there's a problem with this assumption. And the problem with this assumption that the very first data value will be 1 divided by n probability, cumulative probability. What's that assuming? It assumes you don't know the absolute minimum value. You don't actually know or record the 0 cumulative probability value. Now let's think about the other end. At the other end, you reach a point where you've got n divided by n. The final data value, the maximum data value, will get a cumulative probability of n divided by n 100%. So you're assuming you know the maximum value in the distribution. That's kind of a problem. The main point is that we often don't know the absolute minimum and maximum value from a limited number of samples. It's not a bad idea to say we don't actually know the absolute min and max when we plot a CDF. And if we wanted to do that equal on both sides, we would use a cumulative probability of I divided by n plus 1. And if we do that, we say we don't know the tails on either side. Now, people will sometimes run into this when they do percentile calculations in Excel. They got the two different types, EXC, I think, or something like that, and inclusive INC. I think that's the two. The difference is with the INC, they assume that the min and max value are the min max value P0 and P100. And with the EXC, it assumes that it does not know the absolute min and max value, and it makes this assumption if you're outside the range of data, it doesn't extrapolate for you, it gives you an error. Okay, that's enough about that. So in general, I recommend the I divide by n plus 1, and you can use that. And so now what you have is you have the cumulative probability for each one of the values sorted in ascending order again, and you have the data values sorted in ascending order. Sorry. Now, if you plot them, the cumulative values against the data values sorted in ascending order, you get this plot right here. So what's the thing about this? Well, equal weighting. If you wanted to do declustering, you'd have to incorporate that into the cumulative probability calculation. And there's no bin size assumption. It's at the resolution of the data, which is pretty useful. So I often have students ask questions about should a CDF be continuous, differentiable, so that you can actually calculate the PDF directly from the CDF. Because we know, in fact, that the PDF value will, in fact, be the differentiation of the CDF. And so to us, does it have to be? And does it have to be differentiable or continuous and so forth? Well, continuous, yes, but the CDF may in fact be a piecewise function. And then in that case, the way you work with the differentiation is you work section by section. And so here's an example of that right here. There's a discontinuity here. It's not a jump discontinuity. It's just a discontinuity in the slope. So you'd work from here to here with the differentiation, and then here you'd start over again. And so that's not so bad. What about, should it be something, it's now, I should state that it's okay, it would not be okay for CDF to have a jump discontinuity, because you could be rising like this, you have discontinuity, but it's a jump. And so we know once again that would represent negative probability over the value right here, which is not possible. So what can you do if it's not, the function is not continuously differentiable? Well, you can do it piecewise. You can also use numerical differentiation in order to go from a CDF to a PDF. Okay, so here's an example of building a CDF up. It's pretty straightforward. You got these samples. To make it easy, I sampled them right here. And I will show you the solution in 3, 2, 1. So this is pretty straightforward. For this case, I used the I divided by N because it worked out really, it was just super easy to work with. And so there's 5 data values, 1 divided by 5, 2 divided by 5, 3 divided by 5, 20%, 40%, 60%, up to 100%. I plot them, and you can see the result. And so that would be a simple way to make a CDF. If you do the N plus 1, this would not reach 100% right here, and you'd have tail extrapolation. You notice here I put a dashed line because you have to make a choice about what's the ultimate minimum value if you want to perform extrapolation. Here's an example of taking a PDF and trying to determine whether or not it's a valid PDF. And you'll notice this is very cooked up. It's very, very simple. And so what we have is the depth of the oil-water contact in a region of the reservoir is described by the following PDF. And so it can be anything between 2,000 meters and 2,200 meters, and you notice it's uniformly distributed. Uniformly distributed, as we talked about the distributions before in the videos that I suggested people to look at, we know that that's a maximum uncertainty distribution. We don't know really. It's between 2,000, 2,200. Between that, we really don't know very much. We're just saying equal probability for everything. Okay, go ahead and check to see whether or not this distribution is, in fact, represent a PDF to see if this is valid. And so I would suggest that you're going to check the sum of the density underneath the curve to make sure that it, in fact, sums to 1. And I'll give you the answer in 3, 2, 1. Yeah, I admit it. I made this one super cooked up and easy to do. So what we have to do is we have to check for closure, that the probability, the integration from negative infinity to positive infinity of the PDF, lowercase f, is equal to 1. And so in this case, we'll integrate from, we only have to be concerned about 2,000 to 2,200. The function of the curve is simply constant, 1 divided by 200. We perform the integration, we get 1 divided by 200 times z, or z as we say in Canada. And we go ahead and perform the integration. We calculate the area under the curve, and we will find that that's equal to 1. And that was a bit of a no-brainer. So what about converting this PDF to a CDF? And so this will also be very straightforward. And so just think of performing the integration between negative infinity to x in order to calculate the CDF from the PDF. And I'll show you the answer in 3, 2, 1. So this is the same thing we had before, the oil-water contact. And we're just trying to show the CDF. We know it's a valid PDF. We can go ahead and calculate a CDF from it. And so we're going to do the integration from negative infinity to a specific value. We perform that integration, and the result is we get a function that looks like this. 1 divided by 200 multiplied by z minus 2,000. And so what is it? If you have a uniform distribution, the result is a linear CDF. And that makes perfect sense because if you think about it, for every increment of depth, I'm adding the same probability density, so it's linear. It's very, very straightforward. Okay, now let's one final question here. What's the probability of being between 2,050 meters in depth and 2,150 meters in depth? And I'll go ahead and give you a minute to, or shucks, take as much time as you like. You could even have lunch right now. It'd be totally fine with me. I'm okay with that. So I'll give you the answer. Pause me. I'll give you the answer in 3, 2, 1. So this is pretty straightforward here too, right? Because all we have to do is take our CDF, and you remember what we learned about cumulative distribution functions. You just have to evaluate the value of the function at the upper bound, subtract the lower bound, and you'll in fact get the probability that you're within that interval. And so if we substitute into the CDF equation we calculate, super trivial. I'm sorry, I kept it really simple for this. You go ahead and look at it, you'll find out that you get about 50% probability of being between about 2150 and 2050, and that makes sense. It's half the area, and the PDF was in fact uniform. So that'll be it's very easy to check and know that that was right. Okay, so that was some very simple calculations to support this idea of going between CDFs and PDFs. Let's talk a little bit more about practical use of distributions in the subsurface. How do they get used? And so for categorical variables, the data is going to be pooled, weighted. It'll be weighted by some type of declustering weights accounting for bias. All data sets are biased. In the subsurface, they're always biased. We'll incorporate that. And we go ahead and we pool the data, weight the proportions, and we can go ahead and calculate the categorical probability density function. And so we can go ahead and look at the summary statistics. Now what's interesting, if we take a data set which is categorical, as I said, an example would be facies. And so in a carbonate type setting, we'd have limestone, dolomite, and hydrite would all be possible types of facies we could deal with. Now, this is very interesting because what summary statistics would you calculate from this distribution? We're doing univariate analysis. We're doing our data analytics. What do we calculate? What's interesting from this distribution? What do we calculate? The average? The variance? They don't have any meaning here because limestone, dolomite, and hydrite are categories that do not have ordering relationships. There's not a natural ordering to them. And so if I was to say this is facies 1, 2, and 3, and I calculate the average, and the average comes out as being 1.8, that's not meaningful to me. And so about the only summary statistic of interest to us would be the proportions. 50% limestone, 20% dolomite, and 30% anhydrite would be the thing we're most interested in. You can also calculate the CDF. Now, you could take the calculate the CDF by simply just integrating across this. And if you integrate across, you'll find that 50% are in limestone, 20% dolomite, and 30% closing it out in anhydrite, and this is a CDF. Now, we should note that the ordering relationship is not important in the CDF. We could reverse these and put dolomite here, limestone here, keep anhydrite there. It doesn't matter. And the most common reason that we would do all of this to calculate a CDF would be to do Monte Carlo simulation from the distribution. We'll talk more about that later. For a continuous variable, what are we going to do? How do we go ahead and work with it, build these CDFs up? And so the data is pooled, and we'll calculate a CDF with weights accounting for the data bias and tail extrapolation. We're going to weight the data using some type of declustering type weighting. We're going to assume we don't know the min and max value. We're going to use natural types of constraints like 0% porosity or some maximum rock strength or allowable porosity for the available rock mechanics or rock properties. And we'll work out the upper limit and the lower limit. We'll calculate summary statistics like shown here. We have a CDF. We've got a set of summary statistics. You're often concerned about the degree of spread, the central tendency, specific quartiles maybe, or maybe even the P10, the P90 are pretty common to look at. You can calculate the histogram by binning the data into specific bins, and the histogram is quite convenient to look at, and we may record it based on frequencies. I've labeled the number of samples in each bin right here, but for a predictive model, I'm more concerned with the binned PDF. I want to convert these or normalize these into actual probabilities of being in the bins by dividing by the total number of data, and we'll get a binned PDF, and we'll use that for a predictive model. And so that's a pretty common approach that we'll take. Now what we'll do right now is we'll go ahead and show how to do this in Python, but I think in order to keep this video a reasonable length, I'm going to stop right here with the discussion, record the Python walkthrough in a separate video. This is already 40 minutes. I hope that this was useful to you, that this was a good review of the concepts of histogram, PDF, CDF for the purpose of univariate statistical analysis, data analytics. I am Michael Perch. I'm an associate professor at the University of Texas at Austin. I am working in geostatistics, data analytics, machine learning, and I'm always happy to discuss. You can find me on Twitter, GeostatSky, GitHub, GeostatSky, YouTube, GeostatSky lectures. And hey, if you want me to drop by and see you at your company, you want to collaborate on something, I'm always happy to visit. I'm always happy to help out. So, hey, all right, take care. Bye.